think that Stokes theorem will sound familiar. Now, if you remember, Green's theorem gives us the relationship between the circulation on a closed curve and the region that's enclosed by the curve. Now, here is the region enclosed by the curve, and here's the line integral around the curve, and there's some factor that they are related by, which is called the two-dimensional curl. And Stokes theorem is the same thing, but in 3 dimensions. So here we're told that in 3 dimensions we have the same thing. We have a closed curve that's related to the double integral. Now this is a surface that we're integrating over, and the factor is still called the curl of F. So essentially we have the same two things said for 2 dimensions and for 3 dimensions. Now, just like we've been talking about before, proper orientation is important, and we're going to be using positive as being what we see if we point our right hand in the direction of the curve and our thumb is then pointing towards the surface. Now we're going to be taking a look at this example and see how Stokes theorem applies. I've constructed a graph in Maple of the vector field and a graph of the surface, which is green, along with the curve, which is red. And the idea is here's the surface inside of the vector field. Now, according to Stokes theorem, we could compute the surface integral of that green surface in that vector field, or we could compute the line integral of the red line around the perimeter of that surface, and they should give the same value, and that's what I'll be showing you in just a moment. So let's start by taking a look at the line integral. So here is the parameterization of the curve. The curve x squared plus y squared equals 4 would be the circle of radius 2. And so a good parameterization of that would be 2 cosine t, 2 sine t, comma 0. That would give us a counterclockwise orientation. Now, we want to take the 2 cosine t, which is x, 2 sine t, which is y, and 0, which is z, plug all of those into our vector field and get F in terms of t's. We need to do the derivative of our curve to get r prime, and then do the dot product of F and r prime. We'll simplify that some and a little bit more, and that's a pretty easy integral to evaluate. Now let's see about the surface integral. So here we're going to call the 3 components of our vector field F, G, and H. The definition of the curl is here the partial of h with respect to y minus the partial of g with respect to z, and so on. You can read those as well as I can. So here's what we get when we do each of those and simplify. So the curl of f is 0, 2, 2. Of course, I have a TI-89 program that will compute the curl of a vector field. And we parameterize our sphere like this. Now, the u's and v's are just traditional. You can probably recognize from spherical coordinates that the u is our phi and the v is our theta from spherical coordinates. However, since we only want the top half of the sphere, we're using u to go from 0 to pi over 2. So we'll do the derivative with respect to u, the derivative with respect to v, and find the cross product of those. Now we want to take the curl of f, which we just found, and n, which we just found, do their dot product. Since we were doing the parametric version of our surface, we already know the du dv goes 0 to pi over 2 and 0 to 2 pi. So that dot product comes out to be this. Now I'm not going to go through the details, but again, with a TI-89, that is no problem to evaluate. However, that would take a while by hand, doing the integral with respect to u of sine squared u and sine u with a cosine u and an 8 on it. However, cutting to the point, that comes out to be the same thing that we got when we did it the other way. Thinking probably for this problem, the line integral would be the better way to go. Now, there is a separate video with a similar problem to this showing both ways, which is kind of like what we just did. However, we'll go ahead and use Stokes Theorem. Instead of doing 3 different line integrals, we will do one surface integral on this surface. So the plane can be described as z equals 1 minus x minus y. And if we change that to x plus y plus z equals 1, we can see real easily that a normal vector to that plane would be just 1, 1, 1. It's one of the reasons I chose to do the surface integral for this. The normal is real easy to compute. Now, to compute the curl of f, we do those partial derivatives and combine them together. We'll do the dot product of those two, which is 0 times 1, 2z minus 1 times 1, and 0 times 1. Now that comes out to be just a 2z minus 1. Now we're trying to evaluate this in some region in the xy plane. So we're going to take the plane and substitute for z the 1 minus x minus y. Then we will describe the region that we're integrating over, which, remember, is the projection of that plane onto the xy plane. So here's what it looks like in the xy plane. We have this line going from the point 1, 0 to the point 0, 1, which would be y equals 1 minus x. That means if we integrate this first with respect to y, we could go from 0 to 1 minus x. And then with respect to x, from 0 to 1. Now again, we could type that into an 89, evaluate it by hand, but it comes out to be a negative 1/6. So according to Stokes' theorem then, this line integral along those three separate paths would also be a negative 1/6. Now in this final example, we will just be doing the opposite of what we just did. Instead of computing the surface integral for this, we're going to employ Stokes' theorem, which says we can do the line integral of a curve around that surface. Now I'm going to choose the red line that I've drawn on here in the XY plane, since that is pretty easy to describe. That's a circle with a radius 2 oriented counterclockwise. Since we just did that recently, we know here is our parameterization. So we want to begin by taking our field and replacing the x's with 2 cosine t and the y's with 2 sine t. We need to find r prime. We need to do the dot product of those, maybe simplify some, and then integrate that over the region we've already described as 0 to 2 pi.